Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all to this lecture in this course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. In the past several lectures we have started looking at the spectroscopy aspects. We started with the absorption, UV visible absorption, electronic absorption spectroscopy, and then once that is completed, then we have spent a few lectures on the fluorescence spectroscopy applications. Now let us look at another very important topic in this particular area is the mass spectrometry. So the mass spectrometry now, unlike in the early days, is being used for a variety of systems in the chemical, biological, materials, everywhere it is used. Though 5 to 6 decades back, it is mainly used for very small molecules, organic type, where one would like to establish the structure by looking at the degradation pattern, etc. So now it's no more in that particular arena. Now it has grown a lot. So in order to sort of cover the applications pertaining to coordination compounds, metalloproteins, protein enzymes, and many other, and identifying their structural schemes, etc., we will utilize the two of the major techniques. So one is the electrospray ionization technique. We will cover a reasonable extent on this to cover all these applications. The other one is matrix assisted laser desorption ionization techniques. So these are the two that I am going to cover primarily for all of these, and we will also look at some examples, particularly coming from the nanoclusters, metal ion exchange, all those kinds of things. Okay, so let us so mass spectrometry, needless to tell you, it is a technique which measures the mass. So the mass of an ion. So that means you convert the molecule into a kind of an ion with or without the breaking of it, and then that ion can be either the cationic or the anionic. So you can get the mass for that. Just from the mass of this, you can definitely get information pertinent to the, if you have a mixture in a product, a mixture in a reaction, the mixture in isolated compounds, or from a biological systems where you can isolate the cell extracts. So all of these mixtures can, the individual components of the mixtures can be identified if you don't degrade them, and that is where the technique of these, the ESI and MALDI, are going to help a lot. So it gives a lot of very vital information, because the nature has given us the elements in their the different isotopes, and the different isotopes have got a different relative abundance. So using this as a factor, so you can exploit this parameter. The parameter is the isotopes and the relative distribution of the isotopic abundance. Just using that concept, you can identify huge amount of information from the mass spectral things. Let's say example, I have a complex of cobalt, I have another complex of zinc, or the same ligand, but their isotopic peak pattern for the cobalt and zinc are absolutely different. Therefore I can say with confidence, this is the isotope, this is the complex of the cobalt, this is the complex of the zinc, etc. This is another thing which the blessing in disguise for the mass spectrometry, not just the mass number alone. Okay, so such kind of information can be utilized to identify, to elucidate, to characterize. All of these kind of aspects can be done for the compounds, and all of these parameters will help you in establishing the structure. So how would you do that? Generally it can be a solid, it can be a liquid, it can be a gaseous molecule, but as I said in the beginning, that it has to be an ion. So that means you need to bombard with something, some energy particles, for example electrons. So if you bombard with electrons, they would impart certain energy, they would impart the charge, etc. So, you can make the charge kind of a species with or without breaking or with mild breaking. So, without any breaking or with mild breaking or with a large breaking, depending upon this. So, it is not only the electrons, you can use variety of charged particles. So, number one process is the charging the species. So, one is so your molecule you are charging with positive or negative charge. So, that is one thing. Now, that is not sufficient enough, because that will only cause the enough of the ionizations and then enough of the this kind of a charge species. The two is to separate these charges. This is what is required, separate these charges. So, this is done by the mass of the unit and the charge. So, this is the charge which is present, this is the mass. So, what we use is the m by z parameter in this. So, depending upon that m by z, if you apply a magnetic field and electric field, because of these charge particles will deflect to different extents depending upon their m by z value. So, that means, so you have a large number of ions, then you put under the magnetic field or electric field, then so what you get is beam in this, beam in that direction, beam. So, those which are having different kinds of jet. Now, if you have a detector plate here, you can measure the current, how much of the charge is measured in terms of the current. So, you can get that particular things. So, that is how you can basically. So, you make ionization into charge species, separate these charge species, measure the intensity of each of these, and then at the end what you do is you plot m by z versus the intensity or current okay, for each of this. So, this will give you the mass spectrum on that. So, as I mentioned in the beginning, that I will be discussing in this particular course and under this particular topic, not all the techniques that were very well used for the organic chemistry in the beginning, but the two new techniques of the ESI. This is electro spray ionization. In some books it is written as ES also, but not EI. EI is electron impact, it is a different technique. So, we will not be looking at that at all. We will not be looking at CI, chemical impact. So, those kind of things we will not be looking at. For the ionization, we will look at the ESI or ES, electro spray ionization, and the other one is matrix assisted laser desorption ionization technique. These are the two techniques. They are very soft techniques. They can give the molecules intact with their ionic species, or sometimes even the aggregated species together without breaking the weak intermolecular interactions even. And you can also have a further interaction with these with these charged species. You can break as well to mild to a lot extent, because you would like to have this dissociation is as minimal as possible. So, kindly I draw your attention onto this particular slide. Let us start with one of the technique, that is electro spray ionization, ESI, mass spectrometry, ESI MS. Okay. So, what you do here is, in any technique, you first create the ions, then the ions is separated out, and then you get measured. For example, here the sample in the solution is injected into that, and it can be a protein, it can be any kind of a thing, and it will and you allow it for this to be charged and then broken. So, have a look at this particular slide. So, before we go into this, let us look at this particular scheme that I have on the left middle of the slide. The sample, and you subject to ionization. The ionization technique could be ESI, could be MALDI. I will be taking up the MALDI once I complete the ESI method, maybe in next class later. Now, this technique, when you apply, obviously you are making the species. You can make the cationic, you can make the anionic kind of things. So we are referring to the cationic one, and you can measure these directly by separating them. So that is what is called the MS, the precursor ion. Now if you have a collision induced, that means you have some energy particles which will be breaking them further. So collision induced dissociation, if you allow them, then there will be you can make a separation of that, and they will make into some kind of a fragmenting. So that is what is called as a product, and then you can detect that. So you can detect without much breaking of these pieces, or even with some mild breaking, or with little larger breaking as well. All of these have got different utilities. So again, I draw your attention to look at the top right of the panel, and this will tell you the process of ionization. So you have the syringe or spray nozzle, you can call it as, which is having a solution with this your molecules or species, whatever you have, and this is what you call analyte species. So the analyte species are put like through the nozzle, they form the droplets and they get charged. So you can see here the plus charge, and when you have this plus charge, this as you keep moving, these droplets will lose the solvent and they start shrinking, they become a little bit drier. So that shrinking size, so when you have a lot of charge and the size is small, and from the physics you understand that such kind of a bubble or such kind of a drop will not stay, will not be stable, it will disintegrate. So it will disintegrate, and that is what is called the Coulombic fission. So you get smaller ones, you can see. So in the process of smaller one, you might get even one single molecule or a few molecules which are aggregated still through some weak interactions, that kind of things. It is not a huge fragmentation, but it is just a breakup of the huge droplet into a smaller ones, that is all. And now of course you apply your electric field, magnetic field, separate them, then you can go for the measurement. That is not shown in this, but those will go into the mass spectrometric detector part of it, which is not necessary for understanding this course. So I hope and this is applied with the electric potential difference, and with this positive, that is cathode, and the negative is the anode. So you connect these two ends as a positive cathode and anode, and therefore you have this. So you apply the current, therefore that will give you the electron pre methodology of this. Okay. So we do not need to know the process of separations, process of measurement, etc. in this particular course. The same thing whatever I explained to you earlier in this, also shown in a slightly different format in this. So you can see that this is the nebulizer, and then you have a nitrogen inlet in this, and you push your jet into this, and then droplet, just like the way you have seen here, and these droplets will shrink and then they will break and make. So this is meant for a protein kind of thing. The inside that is shown is a protein, but the principle, the methodology, everything is same. So you apply the positive and negative plates and then potential difference. Now I hope you understand the phenomena of the charging or making the charged species. The rest is all the instrumentation part of it. So that is what is the title comes as the electrospray. So in this, now I have an example, two examples shown on the same slide. Here one of them is shown here as the ESI MS of myoglobin. Kindly look at the spectrum on the slide, and you can see peaks with different heights and going up to the highest and then coming down, like about close to the Boltzmann kind of a distribution kind of thing. Okay. Now you can see different heights, and there are some plus values are written. That means the charge, that is the Z value. This is Z1, this is Z2, etc. So like that you can see that. So these are all coming from the same species, same system, but differently charged, because here when you break up, so differently charged ones, some of them will have 4, some of them will have 3, some of them will have 1, some of them will have 0, but they will not be detected. So neutral ones will not be detected, obviously. So ones which are positively charged. So big molecules, you can get a bigger charge distributed. So this is a protein, myoglobin, which is a protein with a high molecular weight. So the molecule can hold as much a charge as 10 up to a charge of 15, 16, 20, etc. So 10 to 20 also charges, but the number of molecules holding 10 range, the number of molecules which are holding charges like 20 above are very small. The major species are somewhere in between, and neither the 10 nor the 20, somewhere around 15, 16, you can see that. So there is a species distribution, because the greater the charge, this will break down, the smaller the charge, they will combine and then make, so optimal charge. Optimal charge by size of your the species here, and that is what you are finding out. Very huge, it will break down. So you are finding the peaks at different Z values. So you take the m by z from here, from this value, and this is m by z1 is equal to whatever the value you get here. So let me say this is x1 value, x1. So x1 is known number, so you can get m by multiplying that one. So it's very easy, you can see. Okay, on the same slide, please have a look at it. I also have another example for another protein called lactalbumin. So this lactalbumin is showing here with the 8, with the 9, with the 10, 11, 12, 13. So again 8 to 9 to 10 is increasing, the intensity in 10 to 11 to 12 to 13 is decreasing. So again the Gaussian distribution of this. So all these are following the Gaussian distribution kind of things. So the explanation is same. A very low charge, there will be small number of species, very high charge, very small number of species, and intermediate is high, because that is the where it can hold the charge. So the both the smaller will tend to be aggregating, with the greater will be tend to disintegrating, so and result into that. So I hope this is again m by z value, you can get the from the x axis the m by z, and then you can get the m value for that. I hope this process, the two major aspects I have explained in this particular slide. One is the process of making the charge species, other is looking at their mass spectral, which gives the different charge species to the different intensity ratios, from which you can get your mass for that. So the relevant aspect that we need to see in this is what kind of species are generally found. So as shown here and on this particular slide, and you can see, so m generally is written for a molecule is a very general convention. M is not like a metal ion here, it can be a complex. If it is a metal complex, it can be a protein, it can be a nucleic acid, anything is written as m, and that is very standard convention. So you do not need to so much go for the argument of that in this. So most often you use it as a m as a species, m as the your molecule. That could be a complex, that could be a simple, that could be any kind of a molecule, even if you aggregated one, etc. So this is the molecule, and then this cannot be detected. So it has to become, so m plus or m plus h plus, variety of these kinds of things. So you can see here on this slide I have shown m plus is the molecular ion, and you can have m plus h. H has mass 1, so that means is 1 mass more than the m, and m plus 2h plus. So the proton, 1 proton added, 2 protons added, 2 molecules of your molecules added to 1 proton. Here 1 molecule 1 proton, 1 molecule 2 protons, 2 molecules 1 proton. So accordingly the charge will be different. Kindly see that. And not only proton, you can also add something like Na plus, K plus, Li plus, Ag plus, etc. Or 2 of the m can also add to these ones, or they can add to some cationic species like R3NH plus, that is quaternary ammonium ion, positively charged species. So that will add the positive charge to that. So or can be methyl, or can be ethyl, many things are there. Most often this methyl and ethyl, or MNH4 plus, or 2 m's with the NH4 plus. So these are all one, the Z will be 1 here, Z will be 2 here. So again here Z will be 1, Z will be 1, etc. Now is it that only? No, many times you can have many other ways of making the positive charge. Like you have a, in your molecule you have a halide, and if that halide is lost, so halide will be lost as X minus of that, and that can also become positive. So you have a molecule with a M is already having an X. Now if I knock out this X, so this will become M plus, okay. and that is also possible. X could be halide, it could be trifluoroacetate, it could be trifluoromethyl sulfonate, many things. So, when an anionic species is lost from your compound, then your compound becomes a cationic species, okay, or two such molecules with one of the X lost. So, all of these. So, you can see huge number of different types of possible. Not that all of these species are formed in all the experiments. So, some of these are formed depending upon the nature of the molecule and nature of the process. Okay. Now, you can also have negative ion mass spectrometry. So, that is, you can have positive ion MS, you can also have negative ion MS. So, most commonly people use is a positive ion, but it is not that negative ion should not be used. So, here you have M minus H, that means one of the proton is lost. Suppose you have a carboxylic group in your molecule, you easily lose a proton, okay, or a phenolic group is there, it can easily lose proton. So, when it loses the proton, it becomes a minus. Okay. So, M plus Na minus 2 protons, 2M plus X, you are adding some halide ion that can also become your neutral molecule, you are adding a negatively charged, obviously your total species is negative. So, you can have all this. So, now you have seen there are a huge number of ways by which these molecules are converted into the charged species, can be mono, di, tri, etc., all these kinds of things. Okay. Now, you can see here as an example, you are talking about 1 proton added, 2 proton added, 3 proton added, etc., etc. You can see an example is shown, it does not matter which molecule this is, it is just some peptide. So, idea is that peptide has got different kind of a groups. The groups can get attached with the proton. I mean, groups can be protonated. Okay. Now, that is kind of thing. So, what are you seeing? There are 3 or 4 sets of peaks. There is one set of peak with a smaller intensity, little higher intensity. Please have a look at this slide I am showing here with more and with more. And each of these looks like a complex spectrum as here, but not just simple. There are 2 points. I will explain the complexity of this each of this peak later on, but right now you look at this as one peak, this is another, this is another. So, what are you finding here? This mass is 860.5, this mass is 861.5, this mass is 862.5, 863.5. So, what do you find? There is a difference of plus 1 mass unit. So, there is a 1 mass unit. So, you are going from 60.5, 860.5 to 861.5. So, that means you have 1 proton added and possibly the 2 protons added, etc. So, all of these kind. So, you can see here. So, if this is 1 proton, there will be 2 protons, etc., etc. So, you can get all of those, and each one is an envelope. It is not a just single line, but instead you have something like that. Okay. So, this kind of a fine structure has a meaning that we will look at just in a while. Let us I think that is also understood now. I have explained you variety of different charged species are possible to be formed, and I showed you with an example of this. Now, that particular fine structure is known as isotopic peak pattern or distribution. So, therefore, this is the one which is a very characteristic of a particular species, that you have the element that is being present. This is what I mentioned in the beginning of this example. How do we understand that? If you look at the relative masses of different platinum isotopes, you can see 190, 192, 194, 195, 196, 198. So, these are the different kinds of mass which is present in the natural abundance, but those with the 190 mass is very, very low, 0.0002, means you can ignore. The other one is 192, there is also 02, you can ignore, but 194 is 0.97. 0.97 is 97% kind of thing. Okay. So, if you take relatively with respect to this 195 as 1, there will be this. So, relative ratio we are talking about, and then if you take 196, it will be 0.75 and 0.25. So, this means these 4 are reasonably acceptable or kind of a abundance. So therefore you can see the peaks correspond to that. At times you may see this one may not. Now if you look at the palladium, a different ion, so you have this one is almost one can ignore, but then you have one with 104, 105, 106, 108, 110. So these are all different isotopes corresponding abundance here. I hope you are looking at the slide because I am showing the values in that. You look at the ruthenium 96, 98, 99, 100, 101, 102, 104. So and then corresponding relative abundances are given. Is it only for metals? No, you can see for the main group elements. For example, chlorine has got 35 is 1, 37 is 0.3. So these are 1:3 ratio. So 0.3 to 1. So that kind of a ratio. So therefore you can see all of them. Like that almost all the elements, of course even for carbon, hydrogen, but their percentage difference for carbon 13 versus carbon 12 is so low you can ignore the other one. But in the other elements they are very prominent. So and this is like a signature, is like your thumb impression. So for example, if I take to explain this, to understand, look at this slide. I have a cis platin molecule here, the 2 chlorides, 2 ammonia with a platinum. And look at you have a peak at 304, then 303, or let me come from this side. You have a peak at 297, 298, 299, 300, 301, etc., etc., with different kinds of intensities ratios, because these are all coming from the isotope peak pattern of the platinum primarily, which is combined with that of the chlorine as well, or chlorine also. The nitrogen you can probably sort of ignore because 14 will be the highest, and the hydrogen you can ignore. So mainly you will see that, but dominance is by the platinum. Okay. So this isotopic peak pattern, like suppose instead of platinum I have a palladium here, I can calculate that. So I can overlay and see the difference and say this complex is coming from the platinum, this complex is coming from the palladium without any difficulty, without any problem, without any confusion. It's like your thumb impression is checked and then your identity can be made. So compared to another person whose thumb impression will not match with that. So I hope that part is very important. I hope this is understandable that. So that feature is the great boon to the mass spectrometry. Otherwise just mass spectrometry becomes just a number. No, it is not true. So let us look at another example to understand the same phenomena which I explained to you. Again, once again draw your attention to the slide, and this is a reaction, chemical reaction and reaction mixture. This is a negative ion spectrum, ESIMS spectrum. It is a reaction of palladium catalyzed Sonogo-Shira coupling reaction. Now, so this reaction mixture is taken and the mass spectrum is measured. Why? Because you want to know through what kind of an intermediate this reaction is going, through what kind of a species the reaction is going. In order to establish that, this mass spectrum is taken. We know the general mechanism for this, but then species has to be identified. So for example, for this spectrum which is shown here, you have one multiplet kind, and this is obviously the isotopic peak pattern, all these number of lines that you have with the corresponding intensity. This is another peak, this is another peak. Each of the peak has got the isotopic peak pattern associated with it. You can match this because you can easily calculate, because these abundances are known. This will fit for this molecule, this will fit for this molecule, and this will fit for this molecule. You can also simulate the spectrum. For this one is a simulated spectrum is there, and you can compare the simulated with the experimental. So whatever is shown here is an experimental, whatever is shown is a simulated for this particular peak. So therefore isotope peak pattern is a very important signature thumb impression for that particular reaction. How it is going through? It is going through this kind particular compound. So how that compound comes? So let us say you started with a palladium 0 catalyst with a ligand bound oxidative addition, OA means. This is not important for the people who are studying this course, but I am just giving as an information. Okay, and oxidative addition will break your RX and oxidatively attach to the, and now this is connected with this RX with your molecule which you are going to do the reaction. Alkyne is bound. So this is the species which you can find from here, and that is what is happening. And this in presence of the base will rearrange and then undergo the reductive elimination and go back. So, what is that you have to confirm? You have to confirm this species of this, and this is the species which is confirmed. That means the reaction is going through this kind of a intermediate. So, I hope you have seen that, etc. So, what I tried to do in this particular lecture was that to introduce you the mass spectrometry, the kind of techniques that are going to be useful, and their nature, to what extent they can be breaking or dissociating the molecule, kind of a species that are being formed, charged species formed, and the isotopic peak pattern, etc. So, with the concept as well as the example. So, we will continue to look at this in the next class, because we need to further develop on this ESI MS technique through variety of examples, including coordination compounds, the nano clusters, and many more for that. Thank you very much.